Have you ever trained a machine learning model only to find it performs brilliantly on your training data but utterly fails on new, unseen examples? It's a frustratingly common scenario, a phenomenon known as overfitting. Your model becomes overexcited, memorizing the training data's noise and intricacies rather than learning the underlying patterns. Today, we're diving into the secret sauce that tames these overexcited models, regularization. It's a set of powerful techniques designed to prevent your models from becoming overly complex, ensuring they generalize effectively to real-world data, which is the true measure of a model's success. Overfitting occurs when a model learns the training data too well, capturing noise and specific details that aren't representative of the broader data distribution. Imagine teaching a student for a test, and instead of understanding the concepts, they just memorize every answer from the practice questions. While they might ace the practice, they'd likely struggle with slightly different questions on the actual exam. This is exactly what happens with an overfit model. It becomes too specialized, losing its ability to adapt. Regularization acts as a guiding hand, subtly discouraging models from becoming excessively complex. It introduces a penalty for large coefficients or weights in the model's objective function. By adding this penalty, we're essentially telling the model, hey, try to achieve a good fit, but don't get too carried away with making your parameters huge. This encourages simpler models that are less prone to memorizing training examples and more likely to capture the true, generalizable relationships within the data. One popular regularization technique is L1 regularization, also known as Lasso regularization. L1 adds a penalty proportional to the absolute value of the model's coefficients. The unique characteristic of L1 is its ability to drive some coefficients exactly to zero. This effectively performs feature selection, meaning it can automatically identify and eliminate less important features from your model, leading to sparser and often more interpretable models. Closely related is L2 regularization, or ridge regularization. L2 adds a penalty proportional to the square of the magnitude of the coefficients. Unlike L1, L2 doesn't typically force coefficients to absolute zero but instead shrinks them towards zero. This weight decay helps to distribute the impact of features more evenly and reduces the influence of any single feature, making the model less sensitive to individual data points and more robust. The choice between L1 and L2 regularization often depends on your specific goals. If feature selection is a priority, and you suspect many features are irrelevant, L1 is often preferred due to its ability to zero out coefficients. However, if you have many correlated features, L2 might perform better by shrinking all their coefficients proportionally. Both aim to reduce overfitting, but they achieve this through slightly different mechanisms impacting the final model structure. Beyond penalizing weights, Dropout is a powerful regularization technique primarily used in neural networks. During training, Dropout randomly drops out a percentage of neurons and their connections in a layer. This means that each training iteration involves a slightly different network, preventing individual neurons from co-adapting too much. It forces the network to learn more robust features that are useful regardless of which other neurons are active. Early stopping is another intuitive and widely used regularization method. Instead of training a model for a fixed number of epochs, you monitor its performance on a separate validation dataset during training. When the model's performance on the validation set starts to degrade, you stop the training process early. This prevents the model from continuing to learn noise from the training data, preserving its generalization ability. Data augmentation is a particularly effective technique, especially in areas like computer vision. Instead of altering the model, it involves generating new training examples by applying various transformations to your existing data. For images, this could mean rotating, flipping, cropping, or changing brightness. This effectively increases the size and diversity of your training dataset without collecting new raw data, making the model more robust to variations and improving generalization. While L1, L2, dropout, early stopping, and data augmentation are some of the most prominent, the field of regularization is vast. Other techniques include batch normalization, which normalizes the inputs to layers, and noise injection, where small amounts of random noise are added to inputs or weights. Each method offers a unique approach to discouraging overfitting and promoting better generalization across various model architectures and problem types. The practical outcome of employing regularization techniques is profoundly significant: better generalization. A model that generalizes well isn't just a clever trick, it's a reliable tool. It means your model will make accurate predictions on new, unseen data, which is paramount in real-world applications, from medical diagnostics to fraud detection. Regularization helps build models that are not just intelligent but also dependable and trustworthy in deployment. Ultimately, regularization is indeed the secret sauce to taming overexcited models. By preventing them from becoming overly complex and memorizing the training data, these techniques ensure our models learn the fundamental relationships, not just the peculiarities. Embracing regularization is essential for anyone serious about building robust, high-performing machine learning models that deliver consistent and reliable results in the unpredictable landscape of real-world data.